Hi everyone, this is Remy, and this video is going to cover the Math 124 note outline for section 2.1, which is increasing, decreasing, and piecewise functions, and also applications. First, we're going to talk about increasing functions, decreasing functions, or constant functions. On a given interval, if the graph of a function rises from left to right, then it's said to be increasing on that interval. And then on a given interval, if the graph of a function drops from left to right, it is said to be decreasing on that interval. And then lastly, on a given interval, if the function values of a graph stay the same, from left to right, then it's said to be constant. So let's do this first example. It says determine the interval on which the function is increasing, decreasing, or constant. So just like it says up here, we always want to look left to right. So for increasing, I'm going to start on the left and look at the graph itself. Here's the graph, like that. So when I go left to right, at first the graph is decreasing, and then right here it starts being constant, staying the same, and then right here is where it starts increasing. And we want to look at the x values when we're determining the intervals. So where left to right is it starting to increase? Well, it's starting to increase right here, and the x value is 3. So I'm going to start with a 3, comma, and then we continue going to the right. And where does it stop increasing? It stops increasing here, because then it turns back around and starts going down. And what x value is this? This is a 5. So it's increasing from 3 to 5. And then we have to decide whether we want parentheses or brackets. But if you think about it, these points themselves, when x is 3 and when x is 5, at those exact points, it's not increasing or decreasing or staying the same. They're just points. So we're not going to include the 3 and the 5. So whenever it says determine the interval on which it's increasing, decreasing, or constant, you're going to always use parentheses. So make sure you get that note. So we're going to go from 3 to 5, and that's when the graph is going up from left to right. And then let's go to decreasing. So again, we're just going to start left. Well, this is showing that from left to right, it's going down. And that's from negative infinity all the way up to right here. That's when it stops decreasing. So it's decreasing from negative infinity up to, we're going to use the x value, remember, so up to negative 1. And I'm going to use parentheses. So it's still always left to right, so that's why it's the x values for all of these. So now we're at this point, at negative 1, and let's continue to see if it decreases anymore. Alright, right here, it starts decreasing again. So it starts decreasing when x is 5. So I'm going to put 5 up to, well, it keeps decreasing forever now, so 5 all the way up to positive infinity. And since it's decreasing on 2 separate intervals, we're going to put a union symbol between them. So this is the interval on which this graph is decreasing. It's from negative infinity up to negative 1. It's not decreasing here, it's not decreasing here, and then it is decreasing from 5 up to positive infinity. Let's go down to part C. Where is the graph constant? So that means it's not going up and it's not going down. It's just staying the same. Well, if we start from negative infinity and then start going to the right, we see it starts being constant right at this point. Stays the same until there, and then it starts going up, and then it starts going back down. So the only time it's constant is from here to here. And those x values are -1 up to 3. So -1, 3, and we're going to use parentheses. Now let's go on to relative max and relative min. So the relative maximum is a value f of c for which the point c, f of c is the highest point in some open interval. And what that's really saying is it's the highest point when compared to its surroundings, whatever's to the left and right of it. And then notice that we're saying that the max is this value, f of c, and so we know that this is the y value. So anytime you're looking for a max, you need to say what the y value is, and that will be your maximum. And then similarly for the relative minimum, this is again a value f of c for which the point c, f of c is the lowest point in some open interval. So again, this is the lowest when compared to its surroundings, left and right of it. So to get an idea of what we mean by this, we're going to look at this picture down here. So we got a graph, and we are going to look for the relative maxes and the relative mins. So for max, we need to look for points that are highest compared to the ones to the left and right of it. We start by going down, and then we keep going back up, and then right here, this point is highest when it's compared to its surroundings. So when you compare it to what's to the left of it and what's to the right of it, it's the highest point. And then we kind of keep going back down, and we go up again, but there's no other point like that one. There's no other point that's the highest when you compare it to what's on its left and its right. And then these 2 points here, if you compare these points to what's to the left and to the right of them, these are the lowest. So these would be considered relative minimums. I'm just going to throw in a scale on the y-axis. So let's say maybe that this is 2, and maybe this is at 12. So let's go by 2s. 2, 4, 6, 8, 10, 12. Alright, for the relative maximum, that point is at the y value of 12. So the relative max is 12 when the x value is C2. So the actual maximum that it reaches is the number 12. That would be our max. And then for the relative mins, we have this one at 2, and then this one at 8. So we have 2 relative mins in this graph. This one is 2, and that's when x equals C1. And then this value, it reaches 8 when x equals C3. So we don't know what C1 and C2 and C3 actually are, we just know there's some numbers on the x-axis. So now let's go back to the example we did earlier and see if we can find any relative maxes or relative mins. And then we're going to put that on the top of the next page. So if you look at the top of page 2, it says back to the starred example above. Determine any relative max or relative min. So this is the example that's starred, so we are going to determine any relative max or relative min for this graph here. So for the relative maximum, let's look for points that are highest compared to the ones around it. Well, I don't see any right now. And then right here, this is the only point on the whole graph that's the highest when you look to the left and right of it. So what's the y value? Remember, we're looking for y values when we're talking about relative max and min. So the y value, the highest that it reaches here, is 2. So that's our relative max, and it happens when the x value is 5. So let's write that in. The relative maxima turned out to be 2 when x equals 5. And now let's go back and look to see if there's any relative minima. So we can go down. Here's a point that's low compared to this side, but this point is the same as the one to the right of it, so it's not lower than what's around it. It's the same as what's around it. And same thing for this point, because remember, the relative min has to be the absolute lowest. So since these points are the same, they're not the lowest points. And then we go up and then back down. So there's no point on this graph that you can say that's definitely lower when compared to what it's surrounded by. So for this graph, there is no relative minimum. So we're going to say none. Okay, so let's do another example for relative min and relative max, and then also increasing and decreasing. Using the graph shown of f of x equals this function, determine any relative maxima, any relative minima, when it's increasing and when it's decreasing. So if you plugged in a bunch of x values into this function and saw what each x value spits out for each y value, and you plotted them, you would end up with this graph. And we want to find first any relative maxima. So what are any points that you see that are higher than the ones to the left and right of it? Well, the only one I see is right here. So the actual max itself is the y value. So what's the y value of this point? It's telling us that it's 2.004. So the max itself is 2.004 at x equals, the x value there is the negative 0.082. And then for the relative minima, we do have a minimum this time. It's right here because this point is lowest compared to the ones to the left and to the right of it. So here's our relative minimum. And again, the actual minimum is the y value. So that's negative 1.604 at x equals, so this time the x value is 4.082. Part C, we need to determine when the function's increasing. So remember, for increasing and decreasing, we look left to right, and we're going to tell what the x values are. So increasing, it actually starts increasing right off the bat from negative infinity, from the left, negative infinity, up to the relative max. So from negative infinity, comma, up to, and remember we're discussing x values this time, so the x value at that point we know is negative 0.082. And then after that it starts going down, but then it starts going back up again right here. So I'm going to put union, and what x value does that start happening at? That x value is 4.082, comma, and then we just keep going to the right forever. It's always going to keep increasing to positive infinity. And then part D, when is the function decreasing? So you start looking from left to right, and then here is where it starts decreasing. Up to here is when it stops decreasing, and so the x values for starting and stopping are negative 0.082 is where it starts, and then it stops at 4.082. And remember, for increasing and decreasing, we're always using parentheses. So these are our answers for this example. And now we're going to switch to what are called piecewise functions. These are functions that are defined using different output formulas for different pieces or parts of the domain. And remember, domain was inputs or x values. So usually, up till now, we would only be looking at one function at a time, maybe something that looks like this. Now, we can have multiple formulas within that one function. So let's do an example. It says, consider the piecewise function d of x equals. So this particular function is going to have three parts. So I'm going to have three lines. The first part is 1 over 1 plus x. And this is going to be for the x values less than negative 5. And then the second piece is going to be x cubed, and that's going to be for x values between negative 5 and 10. So negative 5 is less than or equal to x, which is less than 10. And then the last piece of this function is going to just be the number 17. And this will be for x values that are greater than or equal to 10. So a piecewise function can have 2 parts or 3 parts or 4 parts or however many parts it needs. But usually, I think in this class, it'll just be up to 3 parts. And now we're going to evaluate this function at different x values. So for part A, we want to find d of negative 101. And we know that the inside part is our x value. So our x is negative 101. And what you want to do is look for which inequality over here this x value falls into. So is our x value less than negative 5, or is it between negative 5 and 10, or is it bigger than or equal to 10? Well, out of these three, we know that negative 101 is less than negative 5. So we're going to use this function here. So I'm going to put 1 over 1 plus, but remember, we don't want to write x because we're plugging in negative 101 for x. So I'm going to write plus negative 101, and then we just always simplify our solutions. So in the denominator, 1 minus 101 is negative 100. And you could leave it like that. I just like to kind of throw the negative out in front. But in either case, we get that d of negative 101 turned out to be negative 1 over 100. And we knew which of these three to use because x is less than negative 5. Let's go on to part B. Now we want to find d of 4. So this time our x value is 4. And we're going to do the same thing. We're going to ask ourselves which of these three inequalities does this x value fall into? Is 4 less than negative 5? No. Is 4 between negative 5 and 10? Yes. So we're going to use this one. So we know that x is between negative 5 and 10. So we know to use x cubed. So we're going to take the x value and replace it with a 4. So we have 4 cubed. And then 4 cubed, of course, is 64. So d of 4 turned out to equal 64. And lastly, d of 10. Well, if we look at these inequalities, we see the number 10 showing up twice, here and here. So which one do we need to use? We have to use this inequality here because 10 is greater than or equal to 10. This one doesn't have the equals, this one does, so this is the one that includes 10. Well, since we identified that we are in this case, we'll use this expression, and this expression doesn't have any x's in it. There's nowhere to plug the value 10 into, so we just literally leave it as 17. And that's it. So now, let's go on to the top of page 3 and we'll graph a piecewise function.